Okay, so this is the key video about solving a system of n linear constant coefficient equations. So how do I write those equations? Y is now a vector with n components. Instead of one scalar, just a single number y. Do you want me to put an arrow on y? No, I won't repeat it again, but that's to emphasize that y is a vector, it's first derivative, it's a first order system meaning that there can be and will be more than one unknown, y1, y2 to yn. Okay, so how do we solve such a system? Then a matrix is multiplying that y, and the y's are coupled together by that matrix. They're coupled together, and how do we uncouple them? That is the magic of eigenvalues and eigenvectors. Eigenvectors are vectors that go in their own way. So when you have an eigenvector, it's like you have a one-by-one problem. And the A becomes just a number, lambda. So for a general vector, everything is mixed together. But for an eigenvector, everything stays one-dimensional. The A changes just to a lambda for that special direction. Okay, so, and of course, as always, we need n of those eigenvectors because we want to take the starting value, just as we did for powers. We're doing it now for differential equations. I take my starting vector, which is probably not an eigenvector. I make it a combination of eigenvectors, and I'm okay because I'm assuming that I have n independent eigenvectors. Okay, and now I follow each starting value, c1, x1. What does that have? What happens if I'm in the direction of x1? Then all the messiness of A disappears. It acts just like lambda 1 on that vector x1. Here's what you get. You get c1, that's just a number, times e to the lambda 1 t x1. You see that instead of powers, which we had lambda 1 to the kth power when we were doing powers of a matrix. Now we're solving differential equations, so we get an e to the lambda 1 t. And of course, the next, by superposition, I can add on the solution for that one, which is e to the lambda 2 t x2, plus so on, plus cn e to the lambda n t xn. You can see I could ask, when is this stable? When do the solutions go to 0? Well, as t gets large, this number will go to 0 provided lambda 1 is negative, or provided its real part is negative. We can understand everything from this piece-by-piece formula. Okay, let me just do an example. I'll take a matrix A. In the powers of a matrix video, I took a Markov matrix. Let me take here the equivalent for differential equations. So this will be a Markov, give us a Markov differential equation. So let me take A now. The columns of a Markov matrix add to 1, but in the differential equation situation, they'll add to 0, like -1 and 1, or like -2 and 2. Okay, so there is the eigenvalue of 1 for powers is like the eigenvalue 0 for differential equations, because e to the 0t is 1. So anyway, let's find the eigenvalues of that. The first eigenvalue is 0. That's what I'm interested in. That column adds to 0, that column adds to 0. That tells me there's an eigenvalue of 0. And what's its eigenvector? Probably 2, 1. Because if I multiply that matrix by that vector, I get 0. So lambda 1 is 0. And my second eigenvalue, well, the trace is -3. And the lambda 1 plus lambda 2 must give -3. And its eigenvector is, it's probably 1 minus 1 again. Okay. So I've done the preliminary work. Given this matrix, we've got the eigenvalues and eigenvectors. Now I take u0. What should we say for u0? u0, or y0, say y of 0, the start. Y of 0 as some number c1 times x1 plus c2 times x2. Yes, no problem. No problem. Whatever we have, we take this, some combination of that vector and that eigenvector will give us y of 0. And now the y of t is c1 e to the 0t, e to the lambda 1t times x1, right? You see, we started with c1 x1, but after a time t, it's e to the lambda t. And here's c2. E to the lambda 2 is minus 3t x2. That's the evolution of a Markov process, a continuous Markov process. Compared to the powers of a matrix, this is a continuous evolution of this vector. Okay, and now I'm interested in steady state. Steady state is what happens as t gets large. As t gets large, that number goes quickly to 0. In our Markov matrix example, we had 1/2 to a power, and that went quickly to 0. Now we have the exponential with a -3, that goes to 0. E to the 0t is the 1. This e to the 0t equals 1. Just so that 1 is the signal of a steady state. Nothing changing, nothing really depending on time, just sits there. So I have c1, x1 is the steady state. And x1 was this. So what am I thinking? I'm thinking that no matter how you start, no matter what y of 0 is, as time goes on, the x2 part is going to disappear. And you'll only have the x1 part in that ratio of 2 to 1. So again, if we had movement between y1 and y2, or we have things evolving in time, the steady state is, this is the steady state. Okay, there's an example of a differential equation, happened to have a Markov matrix, and with the Markov matrix, we know that we'll have an eigenvalue of 0 in the continuous case, and a negative eigenvalue that will disappear as time goes forward. E to the -3t goes to 0. Good. I guess I might just add a little bit to this video, which is to explain why is 0 an eigenvalue whenever. If the columns added to 0, -1 plus 1 is 0, 2 minus 2 is 0, that tells me 0 is an eigenvalue. For a Markov matrix in powers, the columns added to 1, and 1 was an eigenvalue. So I guess I have now 2 examples of the following fact, that if all columns add to some, what shall I say for the sum, S for the sum, then lambda equal S is an eigenvalue. That was the point. For Markov matrices, S was 1. Every column added to 1, and then lambda equal 1 was an eigenvalue. And for this video, every column added to 0, and then lambda equals 0 was an eigenvalue. Okay, and also, this is another point about eigenvalues, good to make. The eigenvalues of A transpose are the same as the eigenvalues of A. So I could also say if all rows of A add to S, then lambda equals an S. Lambda equal S is an eigenvalue. I'm saying that the eigenvalues of a matrix and the eigenvalues of the transpose are the same. And maybe you would like to just see why that's true. If I want the eigenvalues of a matrix, I look at the determinant of lambda I minus A. That gives me the eigenvalues of A. If I want the eigenvalues of A transpose, I would look at this equals 0, right? This equaling 0. That equation would give me the eigenvalues of A transpose, just the way this one gives me the eigenvalues of A. But why are they the same? Because the determinant of a matrix and the determinant of its transpose are equal. A matrix and its transpose have the same determinant. Let me just check that with A, B, C, D. And the transpose would be A, C, B, D. And the determinant in both cases is AD minus BC, AD minus BC. The transposing doesn't affect. So that is the same as that. And the lambdas are the same. And therefore, we can look at the columns adding to S or the rows adding to S. Now, okay, so this explains why those two statements are both true together, because I can look at the rows or the columns and reach this conclusion that if all columns add to S. Now, why is that, or all rows add to S? Let me just, I'll just show you the eigenvector. That in this case, A times the eigenvector would be all ones. Suppose a matrix is 4 by 4. If I multiply A by all ones, when you multiply a matrix by a vector of ones, then the dot product of this row with that is the sum, is that plus that plus that plus that would be S. This would be S, because this first row, here's A, the first row of A adds to S. So these numbers add to S, I get S. These numbers add to S, I get S again. These numbers add to S, and these, finally, those numbers add to S, and I have S times 1, 1, 1, 1. Are you okay with this? When all the rows add to S, I can tell you what the eigenvector is, 1, 1, 1, 1. And then the eigenvalue, I can see that that's the sum S. So again, for special matrices, in this case named after Markov, we are able to identify important fact about their eigenvalue, which is that it's that common row sum S equal 1 in the case of powers, and s equals 0 in this video's case with, let me bring down A again. So here, every column added to 0. It didn't happen that the rows added to 0. I'm not requiring that. I'm just saying either way, A or A transpose has the same eigenvalues, and one of them is 0. And the other is whatever the trace tells us, that one. Okay, these collection of useful facts about eigenvalues show up when you have a particular matrix and you need to know something about its eigenvalues. Okay, good, thank you.